¿Vale? Hola, buenas tardes. Vamos a empezar entonces vamos a continuar la sesión de la tarde después de los pósters con esta presentación a cargo de Thomas Heckelei. Antes de empezar, quisiera hacer un recordatorio a una persona que no va a estar más aquí. Ya sabéis que los padres es difícil que acepten que una persona, que sus hijos dejen este mundo antes que ellos. En mi caso particular quiero simplemente reconocer a Ana Angulo. Ella murió hace un mes y medio, después de unos 10 años con un cáncer de mama mezclado con una metástasis en los huesos. Ana fue una de las 3 primeras estudiantes que tuve para iniciar la carrera de investigación. Sin esas 3 estudiantes y sin Luis Miguel, que siempre lo recordaré, yo no estaría aquí. Hemos tenido bastante relación durante estos años, a pesar de que el último congreso que apareció aquí, porque estaba en Economía Agraria, fue en el de Almería, 2009. Coincidimos en el avión de vuelta hacia Madrid y hacia Zaragoza. Es duro siempre, aunque se iba viendo poco a poco que se iba consumiendo. Ha estado luchando, ha estado dando clases, hemos estado hablando, deja a sus hijas y a su marido. Así que nada, descansa en paz. Let's go now to this was the bad news, and now good news. The good news is that I have the honor to introduce Thomas. And it's an honor because I met him, not from the name, from papers, whatever, but we have met since 2005 or 6 when we were participating jointly in a European and an Erasmus Mundus master, in which I have the opportunity to participate with Thomas, and we have met several times, and I think we have developed a kind of at least an academic friendship. So for me, it's a real pleasure to introduce him. Thomas is, he got a master and PhD in the Washington State University yesterday, more or less, something like that. And he was also assistant professor for a while in Washington State. And then he moved back, background was in Bonn, and he came back to Bonn. And now he's a professor and director of the Institute of Food and Natural Resource Economics, the institute there. And now recognized he's also dean of the Faculty of Agriculture, which is a lot of administrative thing. It's not that he's here, but for me, is one of the most brilliant agriculture economists which are now in the arena. He brought this kind of you remember that Bonn has been for a long time the center of all the modeling exercises for policy analysis and so on. There's a big tradition since the 80s. And I think he was involved in this tradition. But he has at least some important achievements. One, for the first time, not only economics is taken into account, but also environmental issues. So how we introduce environmental issues in the modeling is one of the. Second, we are modeling living plants or animals. So we have also some physical behavior. And then why not have to incorporate this kind of physical behavior also in the economic models? So when we have the big economic models, and it's one of the issues that he has been developing or contributed to develop, and I think it's a very good opportunity. He's teaching microeconomics, and also is in a kind of it's difficult to find a person who is very good in macroeconomic theory, econometrics, mathematical programming with chaos and all those things. So he combined expertise in all the quantitative methods applied to policy analysis, and he has also a lot of empirical work dealing with environmental issues, policy, developing recently, and trade. Also, he has supervised a lot of students who have very good skills and now have spread all over the world, trying to continue with this kind of skills. So the presentation today is a step further on that issue. So it's okay, when we go to internet and we are looking for a T-shirt or whatever, while we are working the newspaper, okay, we check something, and then okay, we go to our work, and then when we go back to internet, first appears the same T-shirt or the same shoes you were looking the day before. So somebody have introduced some data that you have used, and then something say, oh no, this guy has this behavior. So the machine has something, and that understand that okay, you like this kind of shoes, or you like these T-shirts, and so on. So the idea he's providing here with a seminal paper in the European Review is about machine learning. So how we can let machine process a lot of data and help us to take the decision. And this is a step further from this kind of modeling exercise, and with a lot of the using of artificial intelligence for modeling predictions and for policy, and from the producer decisions is important. And this is the talk about today. So for all of that, but also because of this kind of relation I have with him in the last 6 years, it's been a pleasure and an honor to introduce Thomas in this conference. So Thomas, the floor is yours.
Thank you, Shema, for the very nice words in the introduction. I sort of listened to you, and I thought maybe I never could decide what I really like most in terms of but you could tell that it's really methodological issues in our field that are interesting me, and also bridging things that have not been bridged before. Yeah, I'm really honored that I was invited to this talk, and I'm looking forward to it, and also to the discussions that may come afterwards. And I hope I can give you sort of a little bit of an insight to why we think that at least machine learning can be a nice addition to our toolbox. And the story, and you see here there are 3 names on it. The story is that a little more than 4 years ago, my then postdoc, Hugo Storm, said, Thomas, don't let us not always do Bayesian econometrics for structural farm analysis, for farm structural change analysis. I have these things here with machine learning, what Google does, what Shema already said, and this is really interesting, and we can use it. And I listened to this and looked into this with him. And then a few weeks later, I met Kathy Bayless at the American meetings, and we had lunch together. And then she said, oh yeah, she's looking into the same thing, trying to combine biophysical, spatially explicit, high resolution data with her economic analysis in Africa. And then we decided, okay, we looked deeper into this and started a whole literature review process, but also several applications. And this led then to this review article in the European Review last year. And this is probably also the reason why I was invited here for this topic. Okay, so much for the beginning here. Okay, so I will give, this is because not all will have here, really an idea what machine learning is. A brief introduction, you will see it's quite closely related to what we do in econometrics and regression analysis to some extent. And after I did that, and we sort of know sort of the key possibilities, then I will go through some applications, really something that is at the core of machine learning, where we do prediction, and which is also relevant for us as economists. But also we can use it for econometric type causal analysis. This is a highly innovative and very dynamic field right now to do that. for multi-input, multi-output policy analysis. And last but not least, I come back to the simulation models again. We can also connect it to economic complex simulation models by using machine learning to derive surrogate models. Okay, and at the end, I say a few words where it might go next and what we as ag economists might be able to contribute. So imagine we want to predict something like deforestation. Deforestation is an example we also use in a machine learning course for PhD students. We have a nice data set from Brazil, and this is an area where Kathy Bayliss worked quite a bit. So we want to predict whether a certain grid cell in a map is deforested or still has forest in the next year. So Y is our target variable, as it is called in machine learning, the dependent variable in econometrics. F of X is the function, and the X are the features, so the explanatory variables, the features which we use to predict deforestation in the next year. So that could be distance to road, the elevation, the slope, all kinds of biophysical, climate, weather-related characteristics. And with all these, we want to predict the tree cover, percent tree cover in a grid cell. So we could use ordinary least squares. We all know that. That could be used also like a machine learning tool if you wish. So we assume a certain data generation process, Y equals F of X plus some error term. But the F of X, this function is our linear index, the normal linear model that we use in a simple linear regression. So here we assume we have this X beta, X1 times beta 1 plus X2 times beta 2 and so on. So we minimize a loss function, as it is called in machine learning, that allows us to optimize the fit. And we use these squares, so then we get as an estimate for the regression coefficient, the usual ordinary least squares estimator, B. So there might be a problem with that. What is embedded in using a linear model like this? It's linear in parameters and also with respect to the error term, but we don't worry about that right now. And that has certain implications. So we have constant marginal effects. dy dx is the constant beta. So what does it mean? There is homogeneity across all observations. Across all grid cells, the marginal effect of one of these features is going to be constant. We cannot capture any threshold effects. Maybe deforestation has to have a buildup of all kinds of factors that then lead to cutting the trees in a certain grid cell. There's no interaction between variables. The distance to road always has the same effect, no matter whether there is a steep slope in between and no possibility to get across at all. So these are examples where such a linearity assumption is totally useless for a prediction problem like this. Okay, well, we know what we can do. We can add a lot of variables. If you remember your statistics first regression analysis, then you can add interaction terms, you can add polynomials, squares, cubes, whatever, of all these features. And ultimately, we will predict Y perfectly. We just need to add more of those. So we can make the fit better up to perfect fit. Well, that is a problem, obviously, because we're going to overfit. We will explain or predict things that are not predictable. So we need a guard, some sort of guard against this overfitting. So we need, or what we can do here is to split the sample into a train and a test set. So we only use the train part of the data set to actually estimate our model. And then we use the test sets that we kept aside to check whether our model is any good in predicting. So we do an out-of-sample check of the validity, of the quality of the prediction of our model. And this is a key ingredient of machine learning. We can add parameters, we can make the model more complicated, complex, highly nonlinear with everything, but we have a guard against overfitting because we set aside data to actually check whether it really generalizes to data that we have not used in that training. So, and then you can look at this. This is here now an OLS-based prediction of deforestation. And on the left-hand side, you see two lines. Train is the blue line and test the orange line. So, and what you see on the horizontal axis is the number of variables that we add. Yeah? So this is a huge data set. It has already 80, 90 variables, but we could have added 200, 300, whatever, just by adding polynomials, powers, interaction terms. But you see already when we arrive at 25, up to 25, for the fit in the train data set increases very well, and also the fit in the test data set increases nicely. But suddenly, this breaks down. Yeah, so suddenly there's a drop in the prediction quality of the test data set. So there's no point, because adding any variables will not generalize anymore. On the right-hand side of the graph is simply the same thing, but looking at the prediction error that you make. So there you already see a criterion in machine learning where you stop, yeah? Where you can say, okay, it doesn't make any sense to add these other variables that I considered. It will not improve my prediction quality of the model. So overfitting, avoiding overfitting is an important way or important key ingredient of machine learning. I only told you a very simple story, the train test split. There's actually a little more complicated story, the train development test split. So you can split it in three, and you use one to estimate, to train the model. You use the second to compare different models. Yeah, and then you use the third to see how good your stuff is. So in econometrics, we don't set aside data for testing. We typically rely on other ways to avoid overfitting. So we have theory that tells us there must be a certain structure and only certain variables should appear. Yeah, for some things that might work, for other things it doesn't. Or we assume linearity. Maybe some of you, I've experienced that several times when we submitted a paper, that they said, okay, you might be overfitting, you have too many variables, you should throw out these interaction terms, even if they had a meeting or whatever. So we often assume linearity just because we know it could be a problem if we have too much. So, the concepts that I've told you out of sample prediction and testing is nothing really revolutionary new. Yeah? I mean, in statistics or econometrics, they have known that. Think about cross-validation for many decades. However, things have changed on the other side. So we get more and more data, a lot of so-called big data, or as Kathy always liked to say for the intermediate things, biggish data. So in many contexts, we get scanner data, remote sensing, Google use, yeah, so vast amount of data you can potentially easily access and use. So we can afford to set aside observations for testing. And with this, we can still train highly complex models because we have still a lot of data for the estimation to achieve a very good fit. And we can allow the data actually to determine functional form. That's what we always have been taught. Well, this is really not much we can do in econometrics about it. So, and then the second thing is this is a very complex computational task. Yeah, because you're trying to optimize something by comparing to data sets and having a vast amount of data. So the computer algorithm had to be developed that are efficient enough to be actually able to do this with many parameters and with big data. But it gives us a lot of flexibility with respect to functional form. So in machine learning, we started with ordinary least squares. This function f of x can be many things. Yeah, it can be a very flexible functional form with potentially many hundred thousands of parameters, yeah, if it's needed for the complexity of the problem. The so-called universal approximator function, where we know that they can always get a perfect fit if we just if they give them enough data and let them train long enough. So, but it is the train test split that will allow here to guard against this overfitting that might occur. And I have some mentioned here which are sort of ordered loosely by the effort in training or the complexity. So some things you might heard about before, well, you might have heard about everything here before, but penalized regression, the lasso, the ridge estimation or elastic net, these are also machine learning models where the train test split can help to do a specification. Regression trees, random forests, gradient boosted trees, originally mostly used for classification problems, but they are now used also for continuous prediction. And the train test split sort of guards against too complex tree structures. Deep neural networks. Here, these have layers and nodes and different types of activation functions. And here again, the train test split can help in finding the right structure for having a generalizable prediction model. So more generally speaking, this train test split allows to tune hyperparameters, to choose the right prediction model and to regularize the complexity to avoid overfitting. So just as an example, here the lasso, the least absolute shrinkage and selection operator. I just need to check that I don't get too much over time, but I'm fine. So the lasso is one of these relatively close to ordinary least squares. What you see down here in the formula, don't worry about the details, is it's ordinary least squares, and then there's a penalty associated with the absolute size of a coefficient, or all the coefficients, the sum of the absolute sizes of all coefficients. So it wants to, if it's a high penalty, it wants to get rid of features. So it would throw out correlated variables that don't help much with prediction. So when you go to the graph and you go from right to left, so against your intuition, then this penalty is increasing. And the very right would be OLS. When the penalty is increasing, it's step by step moves the coefficients towards zero and throws them out one by one. And at the end, there will be only one left. That is the most important one with respect to predicting what we want to predict. So when you apply this now in a machine learning context with a train test split, then you will, when you relax the penalty, then you will get more and more variables in. The fit gets better for the train model. However, at some point, not anymore for the test set. So you see the upper line here, it has a minimum at a certain penalty level, and this is where the optimal prediction model is. Okay, so that was a very brief sort of key ingredient machine learning introduction. Well, we talked about prediction. But what we as economists often want to do is really not predict only the why, but we care about how our variables actually affect in reality, in a causal sense, the dependent variable y. Whereas the machine learning folks, they're interested in predicting the y, which is a different objective. So that also means that quite often what is a good job for the machine learning is not a good job for the economist. For example, the lasso creates biased estimates of the coefficient as long as you have a penalty in there. The machine learning people say, well, we don't care about the coefficients, we only want to have good prediction. However, what the rest of the story is here is that we can nevertheless use what they have found and what the resources they have made available, the enormous prediction accuracy possibilities, we can make best use of it also in econometrics. Well, agriculture economists or the environmental economists may be applied in general, but we study the interactions between human and natural or physical, biophysical systems. So something that always interested me, so environmental, biological, physical. So we want to combine physical and socioeconomic data at different temporal and spatial scales. Yeah, potentially large amounts of data, very different structures, high resolution, a lot of big data. And a lot of problems that we deal with, we cannot say that they are linear. Yeah? They are very likely highly, and in a relevant sense, highly non-linear. And we don't have a prior on really what is exactly the functional form. So there, machine learning can be very helpful to tell us, okay, this is what the data says. So like weather shocks on crop yields, yeah, health effects of pollution. These are not simple linear relationships. They are very complex and depend on the context. Yeah, we like to speak so much about heterogeneity and context. Well, what does it mean? It means nonlinearity. Yeah? This is anyway an area where our field is going. We have substantial heterogeneity, actors, space, time, and we have often in the systems we look at not only one output, but multiple outputs. Something I haven't even talked about, also where here machine learning can help. So we learned machine learning is very good at highly nonlinear prediction. Yeah, that itself can be important and useful, also for our activities as economists, and I will come with one example. We can extract predictions from unstructured data. We don't need to put them nicely in observations anymore. Yeah, the machine learning algorithms, they take what they need to predict the why. We don't have to do pre-feature selection or creation. We can use it in causal analysis to predict counterfactuals, because that's what we need to do good causal analysis. It is also very useful in dimension reduction. Yeah, so-called autoencoders or encoders, like MP4 or music format. Yeah, you can use machine learning to actually come up with a very efficient algorithm that does not lose any information. But in our context, we might have large amounts of data that we need to reduce for some reason. We can identify treatment heterogeneity in causal analysis. That's something where the Stanford people, Athy and Imbens, recently have done a lot in developing new methods to actually do causal treatment analysis. We can handle multi-input, multi-output models, and we can use these machine learning models to create surrogate models for complex economic simulation models. And I will explain later. I try to highlight the ones that I'm talking about now that are coming, one of which will be at the end here, the surrogate modeling. And I explain what it's good for. Okay, let's go to the examples. So I have 4. Prediction may be important in and of itself. So this is an application from Kathy Bayless' lab, and they use machine learning to predict food security of households and communities. Well, here prediction is the objective. Why? Because we want to know early, very quickly, who could be in trouble if there is a shock, of weather shock, a market shock, or whatever. So we can prepare for help. So the problem is the ones that might have that problem, there are very few. Now, what you see here in this cake diagram is sort of the large amounts, they are fine. Then almost a quarter, they are borderline, but then less than 1%, those are the poor, the ones that are really vulnerable, that are threatened. And we need to find those, Those are the ones we are interested in. We want to not miss when we do a prediction of food insecurity because they are the ones that need the help. So in a prediction problem, we need to balance false negatives, missing those in need, versus false positives, giving to those not needy. This is, from a human point of view, the lesser problem, but also would be good if we don't give away too much money to those who don't need it. Okay, what did the authors do? They apply machine learning techniques with resampling methods. Well, resampling is especially useful here because you have a very small data set for the ones that are really needy. But with the machine learning tools, you can power up sort of this resampling techniques. You can check whether you really get valuable coefficients from that. And then they use penalty function with which they can adjust the model so it would not create many false negatives, so-called recall. So then they use living standard measurement survey of 3 years weather and price data in Malawi, Tanzania, and Uganda, and then these machine learning models to predict 2 different food security indicators. So then they compare it, and that's what you see now in the example here on the right-hand side. Then they compare it with the traditional approach, logistic regression, that would identify the categories. And what you see here is that, I don't know whether I can go, okay. So you have recall for machine learning and the logistic, and you have accuracy for the logistic and the machine learning. Yeah, the needy ones we get when recall is good. So what you see here in essence, without going into any details, is with the machine learning tool, you can really increase the recall generally without losing accuracy much overall. And so that's the point. So, which is good. And this is sort of a graph that shows really now for specific households in the area here in Tanzania that the miscategorization of the households really goes down when you use the machine learning tool. So you have a lot more correct predictions. So now we move more from the prediction to the causal analysis. So one technique in econometrics to do causal analysis is instrumental variable estimation. If you have a simultaneity between left and right-hand side variables in a regression, then you use instruments. And one example here is Ryan and Sudarshan in 2020. And they look at India, and there's a problem of groundwater overexploitation, and the government rations groundwater, wants to ration groundwater through limits on electricity for pumping. So they were set out to analyze whether it's doing any good. Specifically, they want to estimate the marginal productivity of water, ultimately to say what are the equity and the equity implications of this policy. So one of the variables that definitely affect the marginal productivity of water is well depth, because it affects the cost. The depth of the well affects the cost of water for farmers. However, it's also the other way around. An affluent farmer will be easier for them to go deeper in the well. So there's a simultaneity problem. So they use groundwater prospect GIS data prepared by the government of India, so all kinds of geological determinants of water availability, and they construct an instrument from many variables that describe the rock type, the aquifer type, the distance to faults and fractures, the length of faults and fractures nearby, and all kinds of first-order interactions of them, because there might be interdependencies because of the physical processes happening. And they use the lasso for predicting this instrument out of the enormous amount of data, biophysical data, physical data in this case, that they have. So they get a really good, strong first stage. They would have really had trouble to actually develop this instrument. You see here the prediction of the well depth just by these exogenous physical characteristics variable. So the results here are, in our context, not very important, but they found the policy is questionable. It has some negative productivity effects, but they could only come up with that because they were able to construct a convincing instrument with it. Okay, example 3. So this is work that Hugo has started, and then with us coming through it a while ago, with learning about neural networks. And since he came from farm structural change, he wanted to address issues that he always didn't like about typical farm structural change analysis, where you predicted classes of farm sizes depending on characteristics of the policy and the market and the initial farm structure. So why do we care? How policy affects farm structure? Well, much of agriculture policy is still justified, at least in the developing countries, by the need, but also in other places, need to preserve the family farm. Okay? So At the other hand, we have complex payment systems, based on size and payment caps and whatever. And nobody can do the complexity better than the Norwegians, and this is actually what we have the data here from. So the challenges are multidimensional measures of farm structure. Why should the size in hectare be the relevant structure, the structural element, structure defining element? It could be the economic potential, it could be animal herd numbers, depending on what farm times you look at. And typically in previous analysis, you always had to restrict yourself to a certain variable or two. But here we have some other possibilities. So then we have typically nonlinear policy effects over multiple outputs. There are a lot of interaction between different policies that matter here. We have spatial dependence quite often, competition for land, this sort of thing that happens, or dynamic processes that are really difficult to measure or identify. So why Norway? Well, one important reason is because we got access to a really nice data set. But the full population of Norwegian farms, more than 70,000 geocoded farms from 1999 to present, so over a long time period. Very complex activist farm policy with many different specifications, a lot of regional heterogeneity. So the policymakers there, they update each year negotiations with the farmer the prices or the subsidies they pay for the different activities. And they do it then based on last year's activities. So Norway, you see here in the producer support estimate, which I didn't change the color from, is one sort of in the top categories of countries supporting the farm sector, up there with Iceland and Korea, and much above the EU or OECD or United States. So we picked one policy out of it, and that is the subsidies for sheep. So, and you see that the Norwegians are quite creative. You see here the payments 2014 and the payments in 2015, where a major policy change happened, and they pay different subsidies per sheep, depending on the size of the production activity. So they pay different ones for 1 to 50 sheep, from 51 to 100, and so on and so on. And in addition, they have a total cap on the overall, something that is obviously, as you know, discussed in the EU context or implemented in parts as well. So what you see on the right-hand side in the graph is marginal and average subsidies for the different time period, for the two time periods. So why do they matter? Marginal subsidies matter for asking, okay, should I add another sheep or should I take away another sheep? Average subsidies matter, should I keep the whole operation at all? I mean, should I keep this production activity level or rather go to milk or whatever? So it's a rather complex decision depending on your initial size, how the policy will affect what you do. Okay, so what we did here was fit a so-called recurrent neural network, with so-called long short-term memory cells. I'm not going to explain anything deeper about this because that's anyway something Google can do much better. But it sort of learns the time structure that is in the data. It allows to take information from the past and keep it as much as it is necessary for the prediction of the next year, if you wish. And it's a deep learning thing with many parameters and potentially highly nonlinear functions that are done. So what is the intuition? The cell states, these cells can encode past information. The model learns itself how to encode the information. You don't have to tell it because it is always checked by how well it predicts. And it also learns which information to keep and which to forget. So no need as in a time series model to pre-specify a time structure, a lag structure or anything. And the lag structure can vary across variables. It can even change over time, depending on what happens. Okay, so what is the intuition? An example, farm stops milk production. Then it might not be relevant anymore what was the number of cows that they had in the past, but it might only be relevant for predicting what happens in the future, that they had at some point a milk production. Yeah? So and then the model will learn itself whether what is important, yeah, to predict the next year. So this model was trained, and then we did some simulations. And we did a simulation of two policy scenarios here, going from 2015 to 2016, changing to a flat rate. Okay, so this is the baseline where the small sheep production activities got a lot, the others less, and then you have an overall cap. And then you have a flat rate across all sizes, and then you have one where you really, with increase it's called, strongly support the small sizes. Okay, and then do the simulation, compare the baseline with the two policy scenarios, and look what happens. So we cannot go into any detail here, but this is now a graph, maybe you haven't seen it in this form, that gives now the distribution, the bivariate distribution of the changes in number of sheep going from 2015 to 2016 for the flat rate policy and for the increase policy relative to the baseline. Sorry, relative to the baseline, not to the year before. And down here you see what were the number of sheep previously. So what you see here is for the flat rate, whatever, well, let's take I save a little bit of time here. So for the increase, only the small ones that were particularly supported, they increased the number of sheep. But the bigger ones, above 200 sheep, they all cut down. But then there are all kinds of other effects that we have to go deeper into the analysis we don't have time for right now. But you see, you can really now hear from the distribution of the farms with respect to these variables, see some plausible policy effects. And I come back to this. Here, fodder. Fodder is, by the way, should not be understood as fodder that is now not needed anymore for sheep if you go out, or that is more needed if you go in. It's rather an alternative production activity in the context of milk. Yeah? And you see that the ones that are going out, actually, in this part of the distribution, they do more fodder production. So then there are cereals, which is totally unaffected from the policy directly, and we would have expected that also it will not be much indirectly affected because it's not substituting on the grassland. It is something that's happening on arable land, and we would expect that the model shows that there's not much happening, and it actually does. The spike of the distributions is at zero changes. So the change in the sheep policy really leaves the cereals unaffected. Well, you might say, okay, we knew that, but this model has learned this purely out of data. There's no economic information in it, in the sense that we told, okay, there is a substitution between grassland, no substitution between grassland and arable land, this sort of thing. It has not been told that, it just learned this from the data. Okay, so without any explicit economic information, this recurrent neural network is able to pick up reasonably direct and indirect responses to changes in subsidy. It's able really to model complex dynamic processes, but more complex than standard autoregressive models, and also more complex spatial patterns that we haven't really dealt with here. So, and I should also maybe stress at the end, one of the things is now we have basically predicted the whole farm. We have not only predicted one output, but we have predicted all the activity levels, the grassland under production, the arable land under production, and so on. So we construct in the prediction a whole farm in the next year. So then you can also, with respect to structural change, make your own calculations, what is important for you in terms of the structure you want to look at. Okay, last example. And I don't want to take too much of your break time here. machine learning for surrogate modeling of simulation models. This is work currently ongoing. Actually, yesterday when I sat in the hotel, Lin Mei, my Chinese doctoral student, sent me the current draft version of the paper so I can use the latest figures here. So it's in collaboration also with IT people from Bonn and with Hugo Storm. So what is the general background? So the ultimate objective of the overarching research problem that we have is we want to have a complex individual farm model incorporated in a regional or national scale model. So we want to have the individual models interact in the larger models with each other. And it's supposed to be a complex individual farm model because it's about environmental policies, things like biodiversity that ultimately are supposed to be measured there, structural change impacts, and so on. So we need also this biophysical component. So the problem is that this farm model takes quite a long time to run. And in this larger scale agent-based model, you need a lot of calls to this model because you have willingness to pay calculations for land interaction, land purchase, and so on. A lot of interaction going on. So what we do now is we train a machine learning surrogate model that emulates the farm model, but solves much faster. At least that was our hope, that we could achieve that. The idea was, I mean, I can generate data from my actual model, and I can generate as much as I want. And if I have a good enough machine learning model, then I can train it so well that it behaves like the original model. So the data can be simulated as needed for the desired level of accuracy that we need for the model. So the bioeconomic farm model we use here is the FarmDyn, and you can look at Wolfgang Britt's lab website for really current description, but there are all kinds of publications out there. It's a dynamic mixed integer individual farm level optimization model, and there is currently parameterized for Germany, but things are going on for the Netherlands as well and some other regions. So for our purpose, we let this model run so far more than 160,000 times. And for different price inputs, coefficient inputs, farm sizes, whatever the original distribution in the farm population is the multivariate distribution of farm and market characteristics. We sampled these input data, let the model run, and it throws out production activity levels, investments, whatever, profit. So then we use this data with the inputs and outputs that the model generated to train different types of deep neural networks. The performance criteria, the only one we care about it, the surrogate model has to predict well, because we want to use it in place of the simulation model. So what you see here is the average R squared across, and this is no typo, 248 model outputs. Okay, 248 model outputs, and you see what the blue bars is sort of the share of the outputs for which the R squared is between 0.9 and 1.0. Yeah. So you see here that for one of the more complicated bidirectional LSTM neural networks, don't worry what that is, those are complex ones with a lot of parameters, that actually in 99% of the cases you get a fit of better than 90%. Oh, sorry. And there are some outputs that are more difficult to predict, but this fit is already, I think, quite interesting. So then, well, we also want to have this model perform well for rare cases. And some of these neural networks don't do well, but some are really astonishing. What we have here is the prediction of the rare event of a positive winter or rapeseed area, winter rapeseed area. And you see here in the horizontal thing, 0 to 160,000 to 16,000 test data. Yeah, and very few of the test data have actually a positive winter rapeseed area. And some of these models pick out exactly those and find them. Yeah. So the 6 or 7 cases that actually have this. It has not been used in estimation. This is the test data set. Yeah. But somehow they must have picked up, learned from the other model what matters for having the winter rapeseed area. Okay, in terms of solution time, the other criterion, so the most complex, the least performing in this respect is still 20 times faster than the original model. Our current favorite is 100 times faster. So there is really something to be gained now for the performance overall in this larger scale modeling exercise. All right, so I'm at the end, close to the end. Let's sum up. So there are a number of places where the improved predictive capabilities of machine learning can really be helpful. Generating access to novel data sources, developing more complex models where they are needed, not for the sake of it, yeah? Including also, and this is maybe surprising to some who always think machine learning as a prediction thing, but not useful for our causal economic analysis. It can also improve our causal economic analysis. However, in the context of what we still need to do, have good identification strategies, a theory behind it that allows us to interpret it right. So what we think is happening, or what we also want to do, there might be selection bias issues in novel data that scanner, Google, whatever, that we have to worry about. There is more and more move towards introducing now theory into machine learning models. Why? Because we don't always have big data, that's one reason. And then knowing something about the mechanisms behind this helps also for prediction. But there might also be possibilities to, and even the machine learning folks are going that direction, to learn causal effects. I cannot go deeper into this, but this is really interesting things. Probabilistic programming should be mentioned in this context. Some Bayesian techniques return. This is fun. So, and as I said, further applications towards causal inference are on the way, and the Stanford lab is really good in that direction. So, if you wanted to, if I've sort of created some interest to some of you and you want to learn more, maybe look at the different types of machine learning tools. You could look at our public PhD course on GitHub. You can go through, look at the videos, at the slides that goes into more detail on the different tools, but it's still introductory. Or the overview paper in the European Review I already mentioned. There's another more extended and updated review coming out in the Handbook of Agricultural Economics. It's in print, so it should be, I don't know, 2 months, 1 or 2 months. And there are, however, this is shameless self-promotion. Yeah, there are obviously also other overviews in specific fields, but also general ones by economists and the use of machine learning in the area. Thank you very much.
Thank you, Thomas, for your insightful information. The local organizing committee allowed me to offer 2 gin tonics tonight extra for a question, because we need incentivize people. Economists, we're always interested in incentives. So, you have one. Alcoholic drinks also have a good incentive. Chema. You have a... Tenemos micrófono.
No, we don't hear you yet.
Hola. Right. Just, okay, first of all, thank you very much. You are a very good lecturer, because this is a really complex stuff for people who haven't had contact with this area. And this makes things sufficiently easy to understand that it can be useful. It can be helpful. So congratulations. Let me think about cost of implementation of the method, and think of the possibility of a cooperative, small cooperative. They want to use a methodology for predictions in their context, geographical context. So we are talking about a small, medium enterprise, and is it feasible, economically feasible? I'm sure that in 20 years, everybody, even from your home, you will be able to apply this. But from the viewpoint of a small and medium enterprise, is it a feasible technology at this stage? Thank you.
So, I obviously spoke out of the academic analysis perspective, but you're asking now is the technology of machine learning relevant for small and medium-term businesses? It becomes, I would say, relevant if the benefit exceeds the hiring of a data scientist. Yeah. But it's not necessarily that a firm has to actually hire and do their own analysis to benefit from the machine learning developments. If you think about the increasing automation of agriculture production in terms of robots, there is tons of machine learning in there, where they use it to interpret the pictures they make, but also to then train the robot to do what it's supposed to do. Yeah. And it can be bought maybe as a service from a company. You don't have to invest necessarily in the whole thing. Yeah? Turning to where I started from the academic, there's also obviously a cost of learning this whole sort of toolbox. Yeah? But I hope I tried to also make clear it connects to what we are using anyway, in a fairly straightforward way. But nevertheless, it will establish itself in analysis as we revise curricula in the teaching, step by step, or driven by some who want to do things more thoroughly or want to do it now. However, I must also say, you don't have to be a nerd programmer to do machine learning. There are certain packages in Stata, in R, which are readily available, and they are very off-the-shelf, non-troublesome, like the regression trees, the causal, the random forest, the gradient boosted trees even. This is one of the most powerful nonlinear prediction tools there is, and you have it in Stata. Yeah? So you can use it now just as you use a regression in general. So in that sense, the cost is not that big, but to apply it right, obviously, you need to understand a little bit what you can do to tweak it and for what purpose.
We have another gin tonic waiting for us, no? Okay, then Eva.
So thank you very much for this excellent, really excellent presentation. I think it has been an introductory and high level for all of us, for some of us who are not, have a look at it, but we are not experts at all. I have a question for beginners. So you make this point clear that machine learning deals with big data better than when econometric. Thank you, Rita. And the second point is that machine learning also deals with some limitations of econometric modeling. So I don't know if there is a straightforward answer to this question, but my question is there any rule of thumb to determine how large has to be your data set so that you can apply machine learning algorithm? I don't know if there's...
Yeah, I think I understood the questions. Thank you. It's a good one. I'm afraid I cannot give a rule of thumb because it depends on the complexity of the prediction problem. Yeah? So you saw with forestation model, it can already get pretty good predictions with only using 25 variables and according parameters. Yeah, so it depends on what accuracy you want to achieve, and how many variables, how many complex nonlinear relationships are necessary to catch, to get there. If it's highly complex, what you need to do a good prediction, then you need big data. Yeah, then we talk about thousands of data points or million or whatever. But if the prediction problem is simpler, then you can still use the general techniques of a train test split, to let the data speak with maybe, I don't know, 5,000 data points or 10,000. So it's really that relationship between data you have and the complexity and accuracy need of the prediction task. And so you see, it depends on things, but it's also an experience and might have then to do with the specifics of the data. We know from econometrics, it's always easy to do things well if you have a lot of variation on both sides, on the left and the right-hand side. And this will not be much different here. So it also depends on the distribution of the data. So it's something that has to be learned in the application, but the general direction is clear. You need more data, the more complex your prediction task is.
Hi, Thomas. Thank you very much for the presentation. I'm not very sure if I understood 100%, but my question is, how good is machine learning to identify spurious relationships between variables? Because I remember when I did my PhD with Chema with time series analysis, and we had this issue about co-integration and common trends in the data. So I wonder if sometimes there might be a risk that we've got many variables, but many of them are irrelevant to the problem that we are facing, and some of the common trends or some common relationships that we are identifying actually is just by pure chance or because it's just random, just by chance.
Okay, so let me just say a pure machine learning algorithm is dumb. So it's stupid. Yeah. So it doesn't know whether the value that a feature, a variable has for the prediction of the y is because it's correlated to something that's relevant, or it's itself relevant because of a causal mechanism it has related to what it's predicting. So without any theory on the mechanisms, we're not going to know. And the machine learning algorithm itself cannot tell you. It can only tell you this variable helps in predicting. And in this case, it's then also not random, because if you have done the train test split well, then you can prove with data that you haven't used that this variable is relevant. But this is no indication whatsoever for causal relationship. I can help in overarching identification strategies with ML to get better. So the instrumental variable creation, this was an overarching causal theory-based model to predict the marginal productivity of water. And the machine learning was only one part to instrument an endogenous variable on the right-hand side, the left-hand side, on the right-hand side. Okay, so there are other, in the overview article and also in the handbook, we go more into causal analysis. And there are other ways for example, doing nonlinear instrumental variable estimation with machine learning, using these nonlinear functions. A lot of the identification that we claim for our models is based on our assumption on the functional form, on linearity, and it might be totally wrong, but we have accepted it as a profession that it's fine. There are new developments, graph analysis, causal learning, that come now without the background from economics, where we have dealt with it a long time, that try to now look from the data side to learn causal relationships. So this is, I'm still trying to understand what's going on there, but I interpret it right now more like, so you give certain structures from theory, graphs and that helps learning whether the data are in compliance with it or not. The other thing is it uses things like range or causality. So ideas, some things that can only be going in one direction and not in the other, things like this. But it's a mix of theory, and this is what we should be happy about as economists, that we have to understand what is happening in the real world and also how do people behave, that can help then the algorithms to do much better also in that respect. But this is a long way, and this is sort of at the frontier right now, and still developing in even the high-end papers in the American Review or in Econometrica. A few months later, somebody shows this is not right, and so it's really developing.
Yeah, I want to finish with a short question. I was very concerned till the last diapo, because then what's our role as economists? Because it's a lot of data driven, and my question is, and you mentioned at the end that we have to take how theory has to feed that, and my question will be on the other side. Do you think that this kind of methods, which is able to analyze a lot of data, different time spans and whatever, can contribute to change theory on the way around? So instead of, because when you started the presentation, you have a production function and this kind, and it's because it's a economic theories behind. Do you think that we are going to learn some other regularities that will help us to change a bit some of the theories which are, because we have a lot of data and have something which we use something simplistic, but now we have the power to use a lot of data from the data. Do you think that can be changed a little bit, and our role as economists, our traditional economic theory is going to change because of not machine learning, but this kind of technologies and this kind of thing? This is my question is. You pick up it will be one disadvantage of machine learning. One of the disadvantages or limitations of machine learning in relation to traditional econometrics or whatever. Because you put all the positive things. Can you set a negative things from machine learning in comparison with other alternatives?
Maybe, sorry, I'm not caught the last one. Let me get back to the others first. So one good thing I mentioned is that we don't lose our role in develop or understand in our knowledge in giving our knowledge on mechanisms, in agriculture, in human behavior and economic behavior, because that's necessary to make, under limited data, those algorithms also more efficient and help the machine learning tools. It's also the case, and this is what I understood at least, you were asking, can we also learn theory from the machine learning models? And I think we can use them just as other explorative statistical tools to let large amount of data run and then look at, okay, there are all kinds of interpretation tools that allow us to say, okay, this feature is important, this is not. And then we can ask, okay, why is that the case? And maybe there's something that we cannot explain with the theory. We are currently trying to predict the formation of aspirations of African smallholders across 3 countries, how their aspirations change with ecological shocks like invasive species and COVID and locust invasion. And so we have a theory and we see whether the variables that the algorithms themselves come up with are the ones we would expect. Yeah? And there are others relevant. We already see that. So we are wondering, okay, what did we get wrong, or what are mechanisms that we are missing, or maybe variables that they are correlated with, and so on. So it can also be inspiring in the other direction. Now the last one, I'm not sure. I don't think I got it.
I will wait because it's late, and I think that people some stomachs they are looking for a coffee, and we take 15 minutes of the break. So thanks, Thomas, for your presentations. Thanks to the audience for the questions. Chema, Iva, Anna, you have an extra gin tonic tonight. I talked to Lita about that. And have a good break, and we continue at 6. Thanks a lot.
Welcome. I enjoyed it.
Un momento.